Okay, this would be my recording on my assignment 5b, which I'm going to explain how I'm going to do it. First of all, this is the code that I've obtained um, yeah, to do assignment 5b. So I'm going to explain which steps that I use. First of all, I'm going to perform FFT on the wave file. By doing that, I have to load my wave file into Scilab and set all the parameters and perform fast Fourier transform, and I'm using the absolute value of it. So after that, I want to plot the FFT signal. Next, which is to create the bandpass filter, I'm going to use the digital filter function, which is the IIR, the third order, which is a bandpass BP, and a Butterworth type filter. The cutoff frequency was set to 300 and 3000, and this is the normalization I did, and this is the delta value. After that, I'm going to plot the shape of the bandpass filter as well. The next step will be applying the filter on the signal. So I'm going to use the FLTS function to apply the filter onto my wave file, which is the signal, the sound signal. Then I'm going to divide the length of my wave into two, because due to the Nyquist theorem, only half of the sample can be obtained. Therefore, when I'm plotting, I'm taking the half of my value as well. After doing that, I'm going to plot the signal, and lastly, performing inverse fast Fourier transform on my wave file, again to obtain the original audio file. And I'm going to plot it and save it as filtered wave. So let's run this code. First of all, this is the voice signal, original voice signal. And second, this would be the fast Fourier transform signal, which has two extreme peaks on both ends. There are no negative values because I'm using the absolute values. And then the third one, which is the bandpass filter shape. Okay. And then this would be the filter after this will be the signal after being filtered. So as you can see, this is the FFT signal. This is the bandpass. When this pass through this, only this portion will remain, whereas the one at the end will be filtered out. Right? That's it. And then yeah, after the last one, this would be the signal for after inverse Fourier transform. I'll get this. When compared to the original one, there are some difference with the amplitude, as you can see. Yeah. So to prove that my bandpass filter is working, the answer is correct, I've used a software called Audacity, which is a audio modifying software, so that I can check whether my answer is correct or not. So let's get started. Audacity, and this is my original wave file. This will be the shape. So we are going to apply a bandpass filter, which I'm going to set a high pass, 300 kilohertz, 300 hertz, sorry. And next, a low pass, 3000 hertz. And this is the resulting waveform. And then we'll compare it with the original waveform, which is this original filtered. Okay. So as you can see, the original waveform is this, and the filtered is this. So we can compare the result of the output after being filtered. So we can see this is the peak, which is have a slightly balanced upper and lower amplitude, which is this part, compared to the original one, which has a higher upper amplitude. And then for this part will be this, which has a more balanced upper and lower amplitude compared to the original one, which has a higher amplitude at the top, this part. And the others shows the same shape, like this part and this part, where it's more balanced. Let's see, this part is balanced, whereas this part having a high and quite a steep changes over here, this part. So you can see the similarity between my answer and the one done by the software itself. So I think the answer is correct. So that's that, and thank you for watching.